Hello YouTube, welcome back to another video. Today we are going to be creating our very own self-driving car in Unity from scratch. My inspiration for this video was actually another video on YouTube that showcased this. However, they did not leave any tutorial or any resource on how to actually do this. So I thought, hey, why not? Let's create a video on it. So in today's episode, we are going to be working on one of the 3 scripts required to create this car, as well as setting up the scene and project. Before we get into the code, however, I would like to take a moment to explain how everything works together. I would like to suggest, however, if you do not have a basic conceptual understanding of neural networks and genetic algorithms, please check the description for some high-level information and then come back to this video in order to fully understand and enjoy it. Like I mentioned, the 2 main algorithms are neural networks and genetic algorithms. The neural network takes in the inputs and gives out the outputs. The genetic algorithm will train the network on how to give better outputs. The car controller has 3 sensors, all of which are the raycasts that extrude from the car and hit the walls. These sensors return back distance values from the wall, and they're fed into the neural network. The network manipulates these values and does a bunch of functions on them, and 2 outputs are given out. These 2 outputs are our steering and acceleration value. This is what controls the car. In order to train the car to perform better, we need the genetic algorithm. At the start of the program, 50 random cars are created, each with a random neural network. They each interpret the sensory data in a different way and do random stuff. However, when each of them die, we select the ones that did the best and we combine them together in order to create a slightly more efficient car. So for example, we pick parent A and parent B. We take a few weights from parent A and a few weights from parent B and merge them together to create a child, which should then slightly do better. So we will pick the top 20 cars from the 50 randomly generated cars, and we'll generate around 50 more cars using the top 20 parents. So this is just a high-level overview of how all of this works. There are obviously other factors such as mutation rates, selecting the worst of them. However, we'll go into more of those details when we actually start to code those algorithms. One last thing I would love to do is thank all of my subscribers, because we are on 1,800 subscribers now, and I'm extremely happy with all of the support that I'm getting, so thank you all very much for that. Alright guys, so I'm gonna get right into actually developing the scene now. So before we actually get started into the Unity project, you need to download just one thing down below in the description. It's just 2 megabytes. It's this projectfiles.zip file, and it contains 2 very important files. So one is this plugins folder, and inside you'll find this mathnet.numerics file. This is a library containing a bunch of matrix operations and a custom class called a matrix, and basically we can put in data into this matrix and it will be arranged in the form of a matrix. And we can do a bunch of matrix operations like multiplications, transpositions, stuff like that. Very useful for neural nets, because as you might already know, neural nets are just a bunch of matrices being multiplied and added together to create new matrices. So if you really want to go from scratch, you can create your own multi-dimensional array and do a bunch of manipulations to that, pretending that it's a matrix. But the one thing that these commercial libraries have, sorry, not commercial, this is open source, I think, but these are much more optimized than the classes that we would write ourselves. But if you're comfortable with creating your own matrix class, go ahead. It's not that hard. I've done it myself, but I think this would be the easiest option for people who are just getting started. So if you want to, just go down below and download this. We're going to be using this in the tutorial, but it's not 100% necessary. So I'm going to use this plugin folder and put it directly into Unity, and then I'll be able to use these DLLs in my actual project. You can't use npm to download this library because Unity won't allow you to use it. So you have to use this plugins folder, and you have to get the DLL version of this library. So I've provided that down below in the description, so be happy, like I'm happy for you to use that. So the second thing that I've included is this Blender file. this is the course file that we're going to be using to train our actual car. I've specifically designed this so it has some straight sections, some left turns, and some right turns, so it is able to learn the different types of turns and variations of movement. Because if you just had a fully circular course, it would only learn how to turn left. It would never learn how to go straight or how to turn right. So I've created this so it has exposure to different types of turns. First, we're going to start with the easy straight, and then we're going to teach it how to turn left, a bit more of straight, and then it's going to turn right. And it's just going to have exposure to the different types of turns. And that's good if we want it to be trained on other types of courses as well. Okay, so enough of that. I'm just going to import all of this directly into the project. I highly recommend downloading this. So I'm just going to put this in now. Just wait for that to load. Oh, sorry, it's off the screen. Right, there we go. Okay, so first thing that we're gonna do, I think that Unity has done this for me by default, but on yours you may recognize that this is actually visible. So first thing we're gonna do is we're going to select this cube 001, and we're going to disable the mesh renderer, and we're going to add a mesh collider. So this is to check when the car actually collides. So the next thing that we're going to do is we're going to bring both of these, the mesh collider and the actual course itself, we're going to bring it down because you can see it's off the ground. That's my fault for designing like that, so I apologize for that. We're just going to bring it down so it looks a bit more natural. And sure, go ahead, please change these colors, they're hurting my eyes, but I don't want to waste too much time on that. I just want to get right into the actual important code. Before we can do that, however, we do need one more asset. We're just going to go into the asset store, just search up car, and we're going to take this first car. It's fully free. Let's just download that, and we'll bring that into the project. Wait for a second when this imports. If you didn't understand anything in the introduction, by the way, don't worry, I'll be covering everything in detail as we go through the scripts. So if anything confused you, don't worry, but if I don't explain anything well in my future videos, please feel free to just put all of your questions down below in the comments, and I'll answer every single one of them. Let's go into vehicles, find a Jeep, and let's just drag this Jeep directly in. You might see that it's very small, so let's just increase the size on that. Just make it a natural size. I'm not going to worry too much about the level design on this. Just make sure it's fits the road and like kind of feels natural. So I think that feels like a decent size. I'm just going to put it right there and drop that down. Make sure it's not touching the ground. We're not going to be adding any realistic wheel colliders or anything. We're going to be directly just adding a box collider and moving the transform of this car. I know that some of you might not like that, but if we add wheel colliders and stuff like that, it just gets a bit too complicated. I'm just going to make sure that car's not automatically colliding with this. No. Okay, so let's just disable this again. Alright, so the next thing we're going to do is we're going to add a collider to the Jeep. So let's just add a box collider. I want it to be on the parent, so I know this may feel weird, so we're just going to edit the collider to actually fit the bounds of the car. I want it to be attached to the parent so we can add the neural net code directly to the parent. So just go into the different axes and make sure that the bounds of the box collider are... Oh, this is going to be hard to see. Okay, let me just go into top view. And I know this is not supposed to be done this way, but I'm going to do it like this because I want direct access to the box collider from the parent. So you don't have to do it like this. I just enjoy doing it like this, and I know it's not right, but it's fine. We're going to just put the box collider on there, make sure it's not going too far away from the actual bounds of the mesh. So just going to make sure it's on the approximate outline. And now that that seems alright, we just have one more thing to do. We're just going to add a rigid body. We're going to disable use gravity. We're going to change the collision to continuous, and we're going to constrain the rotation and the actual yeah, not the position. We'll constrain the rotation. Okay, now once we've done that, I believe we have set up the actual scene. Let me just change one thing real quick. So this is the material of the ground. I really don't like this. It's really hurting my eyes. So let's just really quickly change it to a darker green. There we go. Yeah, something like that doesn't hurt my eyes too much. Once we've done that, we just have to add the car controller and we can get started into the actual script. So let's just call this car controller. As you can see, this is not the first time me recording this script. This is like my 20th attempt. So let me add this car controller real quick. Let's open this up and let's get right into that code. Alright, so now that we have set up the scene, let's actually set up these variables in the car controller so we can get right into actually scripting it. So I'm just going to add two private vector 3s, start position and start rotation. Both of these will preserve the start position and start rotation at the beginning, so every time the car dies or crashes, it will reset back to this position. The next thing we need are between -1f and 1f, and these two variables are the acceleration and turning values. We'll just call this a and t. The next thing that we need is the public float time since start. This will just keep track of how long it's been since the car has started. So the reason we use this is to check if the car has been idle for too long, and if it's been idle, that means that the car is useless. So we just reset the network and let's restart it with a different car. So that's the reason for the time since start. The next one is all fitness calculations. So if you read anything about the genetic algorithms, you would know that the fitness function is how well a car or like an entity does in its round. So like in our case, our fitness function is how far it goes and how fast it is. Both of these things contribute towards how the score of the car, you can call it the score of how well it did. So we need three variables for this: public float, overall fitness, public float, distance multiplier, and I'll just explain this in just a second. Public float average speed multiplier and 0.2f. Okay, so the distance multiplier is how important the distance is to the fitness function. So we'll just multiply the distance by this value. And then the speed multiplier is how important the speed is to the overall fitness. So these are the different contributions. So for us, we value how far it goes instead of how fast it goes. If we bump up these this value and lower this value, the cars that go the fastest will be valued. It won't necessarily go as far as other cars, but the cars that go the fastest will be valued the most. So this is just to give importance to each factor. Obviously, speed is one factor that's important. So if two cars go the exact same distance, how do we differentiate which one's better? So we know now that the speed will also have a small impact. So if both cars went the same distance, we pick the car that went the fastest out of those two will have more weight than the car that went slower in the same distance. So that's just a slight little addition that I've made that sometimes proves quite useful. So a few more things that we need is private vector 3 lost position, private float total distance traveled, and private float average speed. And then we need private float A sensor, B sensor, and C sensor. Okay, so basically these sensors are the three different sensors that I talked about. Each one each of these floats just contains a distance of between the origin of the ray to the position where the ray hit the wall. So these are just distance values of each sensor, and these are going to be the inputs to our neural net. Okay, so now let's write the awake method. Oh, by the way, these privates are just basically used to calculate the fitness. So let's create the awake method. So private void awake, and let's just assign the start position to transform.position and the start rotation to transform.Euler angles. We're just going to use Euler angles. We don't have to use the actual rotation component, because by using this, it's just a bit easier. It doesn't really matter what we use. So we're going to write a public void reset now, and this is our reset function. Every time we die, we're going to push it into this reset function, so all of these variables will be reset to its original values, so that nothing from the previous car is carried on to the next car. It's actually quite an important function, so we need to make sure we get this right. So we're going to set the time since starts to 0, and the total distance traveled, we're going to set that to 0 as well. The average speed, we're going to set that to 0. We're going to set the last position to the start position, and we're going to set the overall fitness to 0, and most importantly, we're going to set the transform dot position to the start position, and the transform the Euler angles to the start rotation. Okay, so that is our reset function done. Now let's create a death function. Actually, no, we don't need a death function yet. We'll only add that when we have our genetic algorithm, so we don't need that just yet, but we do need an on collision enter function. So private void on collision enter collision, and let's just kill it as soon as it hits anything. We don't need to check if it is a wall, because based on our scene, nothing is able to collide with the car except for the wall, so it really doesn't matter in this case. Let's go back, and that's our collision method done. And now we are going to create our move car method. So this is an important method, of course, by the name you might be able to tell. Public void move car float to v float h. Okay, so this is vertical movement, this is horizontal movement, or the rotation and the acceleration. I just named them differently so that we can differentiate between AT and VH. So we just need a few privates for this. We just need one private, private vector 3 input, and basically this whole function here I hard coded. I know it's not best practice to hard code stuff, but I can explain it to you. But these values are what felt natural to me, and you can definitely change these values based on what you think is right. So I'll just write it out first, and I'll explain each line by itself. So private vector 3 dot 0 and new vector 3 11.4h. See, these values 11.4h and stuff may not make intuitive sense because I hard coded these values. Okay, so basically what I'm doing here is I'm looping between so this is variable outside of move car, so this actually stores the value from the previous, and what I'm doing is I'm looping between vector 3.0 and this acceleration value times 11.4, a value that I decided to get the correct magnitude of acceleration. I'm looping between this value and this value at a rate of 0.02 f. I hope that makes sense. If it doesn't, I'm sorry. I really don't know how to explain how I came up with this. It was just a bunch of tweaking because the car went too fast sometimes. The car would accelerate like a bit too uniformly sometimes. So these are values that I just played with to come up with. So I'm also going to change the transform direction to make sure that the input is relative to the car. These are basic Unity functions, so if you don't understand these, I would highly recommend just playing around with the Unity a bit more before you come back to this tutorial. You should probably search this up, because what this does, I'll try and explain it to the best of my ability, but if we have an input given to us which is forward, what we can do is let me explain this best I can. If we have the vector of where is it? 0, 0, 0. So if we have the vector 0, 0, 1, this is going forward in the z direction. This is going directly forward, but this doesn't necessarily mean forward in terms of the car. This is just forward in global space. So if we want to convert this forward to local space in terms of the car, we use this function and transform this vector from 0, 0, 1 to what is forward in terms of the car. I hope I explained that well, but basically what I'm doing is I'm converting the input into what's relative to the car. So this is forward in terms of the car. I hope that was explained decently well. I'm not too sure, but yeah, that's basically what I mean. And the most important part, we're just going to say transform.position plus equals input, and that should work fine. And the next thing is the rotation, and this is going to be even weirder, but let me try my best to explain it. This is probably the only code that is probably a bit shaky, but the other stuff I should be able to explain relatively well. Okay, so it's lots of people don't know about mathf.lerp. It's basically like using vector3.lerp, except it's for a float only. Okay, so this makes no sense because I could have just done h times 90 times 0.02f. In fact, I'm gonna do that right now. Let me just get rid of this. Okay, so these are values that I found worked. I keep the times 90 because it tells me what I'm actually doing. This is the percentage of how much I turn 90 degrees, if that makes sense. So if h is 1, then it would fully turn 90 degrees. If h is -1, then it would fully turn -90 degrees. But you don't want to do that instantaneously. Since we're adding, we don't want to do that instantaneously, because if we do that instantaneously, then it would look super unrealistic and it would just jitter all over the place. So in order to smooth that out over time, I have added times 0.02f, another value that I found worked, and yeah, I've added this to smooth it out over time. I hope that explains it. If there are any discrepancies in my explanations, please leave it down below in the comments and tell me what I'm doing wrong, and I'll address it in the next episode. That goes with any of my code as well. Please feel free to point out any issues, because I make issues. I make quite a few problems. Like in my old videos, lots of people in the comments were very supportive, and they helped me out and helped fix issues in my code, and it was really helpful because other people with the same issues were able to look at the comments and just fix their own issues. So if you find any problems in this code, please leave it down below in the comments. Okay, so the next thing that we are going to do is we're actually going to create the inputs. So the sensors that go out from the car hit the wall and return back the distance values. So let's create that right now. We can make this a private void. We'll just call it private void input sensors, and we'll add the 3 vectors that are going to act as our directions. So let's add a vector3a, and we're gonna make this equal to transform.forward plus transform dot right. If you don't know what that looks like, I should probably normalize that, but it doesn't matter too much. We are basically saying work, please compile. Transform.forward this way and transform.right is this way, and we're just adding these two, and it would result in a vector going this way. And then if we say transform.forward minus transform.right, which is going this way, it would result in a vector this way. So we have a vector going this way diagonally, and one transform.forward which goes this way directly forward. We don't have any values going directly off to the sides because, I don't know, it didn't make too much sense. Since the car is only accelerating forward, I thought, why not have values that go diagonally instead of directly to the sides? Yeah, because I mean, you don't look sideways when you drive, right? You only look into the diagonal left, diagonal right, and directly forward. So that's what I thought made the most sense, and that's what I did. So vector3b is equal to transform.forward. Don't know why I put brackets there, it looks good. Vector3c transform.forward minus transform.right, and this is the diagonal left. Okay. Make sure that you understand these are all relative to the car. I'm not using vector3.forward, I'm using transform.forward. Just a quick distinction there. Now let's create the different rays. We're just going to say ray r is equal to new ray from transform.position to in the direction a, and then we're going to initialize ray cost hit. I'm just going to call this hit. And the next stuff is really relatively simple. Physics raycost r out hit. Okay, now one very important thing here before I write this code, you may be a bit confused. Actually, let me write it out before I explain it. Is equal to hit.distance divided by 20. So why am I dividing by 20? Well, in my experience, we need to, well, not in my experience, this is normal, but when we pass in values to a neural net, we need to make sure that it is normalized. So in order for it to be normalized, we need to give it values between 0 and 1, or -1 and 1. We can't give it values above that, because when it gets multiplied by the weights and then the sigmoid function is activated, activates those numbers. If it's too high, then the values will be clamped to either 1 or 0. Okay, so we need to make sure that the values given into the neural net are always between -1 and 1 or 0 and 1. So this divide by 20 just ensures that the inputs are not too large when passed into the neural net. Actually, we're going to print these out to ensure that the new course size, because I just put this course in, I didn't really think about it when I added it in. So we're just going to make sure that the distance values stay relatively close to 0 to 1, okay, or -1 to 1. We don't want it to go too far into the negatives. Obviously these are distance values because they won't go into the negative. We need to make sure that these stay relatively close to 1. It can be around 1.2, 1.3, it doesn't really matter. We just want to make sure it's between 0 and 1 approximately. So I'm just going to say I'm going to print out a sensor. I hope that explains something. So when we actually go to the neural net phase, I'll explain exactly why it's happening. But if you pass in a value of say 100 into the inputs, when we activate it, so the activation function will take any number and squeeze it between a value of a given range. We're using the sigmoid function, which will squash it between 0 and 1. When we do that, if we pass in too high of a number, it will tend towards 1. It will tend towards 1 all the time. So if it's always tending towards 1, it will never have any diversity in its movement. Okay, so it's hard to explain, but when we actually get to the neural net stage, I promise I'll explain it to you. But I'll just print it out to show you that it stays between a value of 0 to 1. If not, we'll just modify this divided by 20 value to ensure that it does. Okay, so once we get the A sensor value, we need to get the B sensor value. So we're just going to change the ray direction. R is ray. By the way, we initialized it here. So we're just going to change it B direction to B. I'm going to say, I'm just going to basically copy this whole thing again. This is the same thing. We're just going to copy it. We're just going to say B, B, and yeah, basically the same thing. And we're going to copy this. So we can copy the whole thing and just put it here, and we're going to change the direction to, you guessed it, C, and we're just going to change this to C sensor, and we're going to change this to C, and there we go. Our input sensor function is done. The next thing we need to do is we need to calculate the fitness. So in order for us to do that, let's create another function. Yay. All right, function. My voice is dying right now, but I got this. All right, private void calculate fitness. Okay, total distance traveled plus equals vector3 dot distance between transform dot position last position. So every frame we set the last position to our current position, and what happens is we calculate the distance between the position last frame and the position this frame, and hopefully we should get a small distance value, and if we add that over time we should get the complete distance. Someone please tell me if my logic is wrong in the comments, because I'm not sure. I've been using this, it seems to work well. We don't need an exact distance value, we just need a metric to compare each car against each other, and as long as this works, it works. Doesn't matter too much, but if there's something glaringly wrong with my logic, please tell me. Average speed, we're just gonna say total distance traveled over time since start. I know this is average speed, not instantaneous speed, but instantaneous speed would not help us in our case. Overall fitness is going to be calculated. This is a long function, so this is going to be calculated through total distance traveled times our distance multiplier, giving importance to our total distance traveled, plus our average speed, times average speed multiplier. And now there's one more thing that I forgot to add. This is another variable that I forgot to add at the very start, and I thought that this was unnecessary, but I'm starting to realize that we actually did need this. So let's just add this: public float sensor multiplier. So basically what this does is it tells our car how important it is for it to stay in the middle of the track, so far away from obstacles. It's not that important, but it would allow the cars that are not crashing into the walls to have slightly more importance than the cars that are crashing into the walls, if that makes any sense. So the way we basically calculate this is we just find the average sensor value, and we divide this by we find the average sensor value, and then we multiply it by the sensor multiplier. So this is a weird function, but I'll do it anyway. Like this, we're gonna do this and A sensor plus B sensor plus C sensor divided by 3 times sensor multiplier. I hope you see what's going on here. I'm just finding the average of the sensor values. I'm multiplying it by the sensor multiplier. Okay, so these values, these three values, will give you, these three values right here, will give you an insane amount of control over how you want your cars to evolve over time. Do you want them to be in the middle of the track most of the time? Do you want them to go faster? What do you give importance to is what we're emphasizing here. Okay, so the next part is our actual detection of if we have a dumb network or a really smart network. What do we do? So what we can just say here, if time since start is greater than 20 and the overall fitness is lower than 20, and the overall fitness is lower than 40, then we can just reset the network, because it's not doing anything, right? It's been 20 seconds and the fitness is only 40. By the way, you will see how the fitness works in just a second. The 40 is really small. Okay, and if overall fitness is greater than or equal to 1,000, this means it's done at least 3 laps of the full course, then we can just reset. But we can also do another function here later on that saves the network to a JSON file, okay? And then we can deserialize that network later on, and then retrain it on a different course. Okay, so by the way, you might realize that all of these values are just hard-coded, trial and error again. If you want to make these variables, play around in your own course, go ahead. I'm 100% that these values, this value, and this division value won't work if you're going to create your own courses, because they won't be the same scale as mine and they won't have the same type of curves. So you might want to play around with these values if you have your own course, print it out like I did, and make sure that the sensor values stay between 0 and 1. Now the most important function out of all of them is the fixed update, and we're going to do it in the fixed update so that it happens uniformly across all frame rates, because we don't want it to change per computer. We need it to be constant. So private void fixed update. Again, please tell me if my logic is wrong. I thought that putting it in the fixed update made sense because we want a constant and stable training environment. So I'm going to just call the inputs first. I'm going to set the last position and make that the transform.position. Does that make sense? Yes, that doesn't make sense, because we're setting the last position now, and then we're going to move the car, then we're going to calculate the fitness. So the car should have moved by the time we check the distance between the last position and current position. Yes, that does make sense. So we're just going to say move car A and T, and we're going to control the A and T values in the inspector. I know it's really unconventional doing it this way, but later on what we're going to do is we're just going to assign the A value and the T value directly from the neural net. So put neural network code here. Okay, and the next thing we're going to do is we're going to add time since start plus equals time the delta time, and we're going to calculate the fitness, and we're going to reset A, and we're going to reset T as well. Okay, actually we're not going to reset them for now because we need to play around with them in the inspector. Alright, if I'm right, most of this should work and we should get a nice little print telling us how our fitness is going, sorry, our inputs are going, and we need to make sure they're between 0 and 1. That's our main thing, and I don't have a camera. That's awesome. Let me put a camera in there. And if you haven't already, let's center out, let's make this camera a child of our Jeep. Center it out. Going to rotate it. Wait, 0, 0, 0. And bring it back. Bring it up. Bring it down. There we go. Something half decent. And as you can see, our A, B, and C values are between 0 and 1, which is great. They're around 0.2. That means our input values aren't going to be screwed up. So I can remove these now because I know these are working. If you're getting something crazy like 2 or 3, that is crazy. I know it's not that big, but if you're getting something like that, please increase these values so that the values become smaller. If you're getting something too small, like 0.00001, decrease the division value so you get higher values. Okay, so just make sure you're getting a reasonable input value. That's very important, or you're not going to get a proper trained car. Okay, here is all of our stuff happening right here. Again, I'm sorry. Here is the overall fitness. And you can see it's not moving right now. Let's increase the acceleration value a bit, and you can see that our car is moving now, and we can turn the car using this steering value right here, and you can see that it feels kind of natural. It's not too crazy, but we can see that the fitness value is increasing steadily, and we can play around, and we can see that the collision is working perfectly. Alright guys, that brings this video to a wrap. In this episode we have created the car controller, and I explained to you the basis of this entire series. I hope you enjoyed, and I hope you can tune in for the next episode as well, where we'll be actually coding the neural net. That's the most interesting episode, and the episode after that is also extremely interesting, actually training the neural net. There are not many videos on YouTube that actually cover these topics, and especially with a self-driving car in Unity, it's really special, and I really want you guys to be part of it. So I hope you enjoyed, and until next time, stay awesome.